So what I'm going to do today is I'm going to talk about how you can use rolling sphere analysis for large and complex structures. And what this presentation really is, it's a summary of some of the things we've learned over some more challenging projects we've had over the last year or two, looking at some larger petrochemical plants and other complex larger sites. And the other thing we're going to look at is some of the complications associated with taller buildings. So certainly in the UK, the general approach to lightning protection for simpler structures has always been to use the mesh method, where you just roll out a load of conductors across the roof and you drop them down the side of the building, and you do it according to the mesh spacing that's driven by the level of lightning protection you require. And in theory, it's quick and easy because you don't have to really coordinate your lightning protection with any other trade as part of the construction. And so for a lot of people, this has been how lightning protection has worked for a very long time. And for simple kind of cuboid structures, it works pretty well, but it has some issues really. And particularly what you're doing with these simple mesh lightning protection systems is that you're inviting lightning energy very close to some sensitive structures. And therefore it means you need to have type 1 SPD, which are quite expensive. And depending on how your building is constructed, you also potentially have the risk of puncturing your roof. Consequently, it's not really cost effective for tall structures. And if you've got any sort of explosive atmosphere, it doesn't necessarily comply with your local regulations for dangerous substances and explosive atmospheres. In the UK, we have a set of law called the Dangerous Substances and Explosive Atmospheres Regulations. In parts of Europe, there's the ATEX directive, and they all have fairly similar requirements. Other parts of the world will likely also have similar rules, but that's, I suppose, not something we've particularly worked on. So, as I say, why do we do it this way? Well, certainly in the UK, it's how we've always done it. It doesn't require a huge amount of coordination, and it complies with the standard. Drawing a mesh lightning protection system across a building is fully compliant with the standard as long as you do all the other things that it says you have to do. But we've already identified a few issues. So what's the alternative? Well, we can deploy what are called isolated lightning protection systems, where we use finials, air rods, whatever you want to call them, to take the lightning away from sensitive structures and conduct it in such a way that it has less of an impact on the operation of the building. And these are some sort of typical examples of the deployment of air rods in what I suppose is a hybrid lightning protection system, where there's some isolated element, but it's all kind of cross-bonded to the structure. Or in this not very good quality photo, you can see the lightning protection arrangements that NASA used to protect their rockets from being struck in Florida. And you can see here they have a fully isolated lightning protection system. And there's a quite nice photo here that shows it being quite effective in terms of interrupting that lightning strike. And generally, A better solution is this sort of hybrid system where we largely have a system of mesh conductors, but we use our air termination rods to protect sensitive parts of the building from a direct lightning strike, and that reduces the risk of lightning to our structures. So how do we design a lightning protection system? Well, Isako's covered this a little bit, but I will go through it again because it's worth getting a good understanding of what you do before you go into Shield, because actually getting that bit right is really critical. So we start by doing an LPS risk assessment, which we then assess the properties of the structures that we're going to protect, and then we apply some sort of electrogeometric method, and then we iterate until we achieve a solution that complies. Now, where we have explosive atmospheres, there's a couple of complications. So in the UK, we need to comply with the dangerous substances and explosive atmospheres regulations. And BSEN 6305 says we must have at least a level 2 lightning protection system where there's a risk of explosion. But we also can't have a point of strike or a joint in our LPS that is within an explosive atmosphere. So that already really limits how we can place our lightning protection system elements to achieve effective protection. And this is where a tool where Shield comes in really handy, because you can do a proper rigorous assessment of the lightning protection system. As I say, most other countries will have similar laws and rules and standards. I'm speaking about European practice because that's what I have the most experience in. Where we have tall buildings, and the IEC EN 62305 says this is for structures that are taller than 60 meters, we need to protect the top 20% against side flashes. So you can see we've got our conventional lightning protection system down conductors, and then once we go above 60 meters, we now have to change to a meshed system of conductors to protect the top 20% of the building against side flashes. So step 1, we do a lightning protection system risk assessment following the approach in IEC 62305. And depending on which country you live in, you might find that there are slightly different numbers. The exact inputs are slightly different because each national committee will have made certain modifications to the standard to cater for, I suppose, local ways of doing things. But the risk assessment is a pretty broad tool. It tries to apply the same approach from pretty much anything from an office building to an oil refinery. So sometimes you have to be a bit careful with the inputs you're selecting, and but essentially it quantifies a couple of different risks. The most critical one for our external lightning protection system is our R1, our risk of loss of human life. We also can choose to consider risk of loss of service. If you're assessing a building like a church where there's some cultural heritage, you perhaps want to assess the risk to that. And finally, there's our risk R4, which is to do with the loss of economic value. And this is a tool within IEC 62305 that allows you to essentially make a cost-benefit analysis of your lightning protection system. And so once we've done our risk assessment, we get some protection measures that we can select that reduce that risk. So we start with our external lightning protection system classification, which starts at level 4 for the lowest level of lightning protection. It then goes up to level 1, and there's a couple of enhanced levels above that which consider sort of denser screening, well, higher screening densities, sorry, than the traditional LPS1. We then provide a level of surge protection measures from level 4 to enhanced level 1. And then there's some other measures which are largely focused on the services that enter the building or the site and how they're designed, and the risk of them being struck by lightning. So we've done that. And what is quite interesting is we then get this table which in a way gives us the effectiveness of our lightning protection system. So we start at this top row where we have no lightning protection system, and that says that if there's a lightning strike, the probability of damage is 1. But then if we put in even a class 4 lightning protection system, that reduces that risk of damage from 1 to 0.2. And so as we increase the level of lightning protection measures on our building, we further and further reduce the probability of damage to our structure. But now we've done a risk assessment, we have a level of lightning protection that we have to provide on our building. And so now what we're going to do is we're going to assess the structures we need to provide. We need to determine what can take a direct lightning strike. There's some figures in part 3 for minimum thicknesses. We need to identify volumes of explosive atmosphere that might require protection. We want to work out if we can use our building structure as part of our lightning protection system. It's quite common to use the steel columns of our building as down conductors instead of providing a copper down conductor. And depending on which part of the world you're based in, foundation earth electrodes might be anything from very common practice to something that is never done. And we also need to evaluate the separation distances so that we can work out what structures, what items need to be bonded to our lightning protection system. And so the first table we look at is this table 3, which gives us the minimum thickness of parts of our lightning protection system. And we've got these 2 columns. We've got our first column here, which gives you the minimum thickness if you want to avoid the risk of puncture. You'll notice that actually this let's say 4 millimeters of steel is actually quite a thick piece of metal. And so what you'll probably find is that standard structural elements don't normally meet this. So if you want a part of your structure to be an air terminal, you will find that it will be at risk of being punctured if it's directly struck by lightning. We also have this T- thickness column, which is for the thicknesses where you're not concerned about the risk of puncturing, hotspotting, or ignition. And so This 0.5 millimeters of steel is often quite useful if you have a building with a sort of conventional cladding system where there's some thin steel on some insulation panels and you're happy that a puncture can be dealt with. But obviously, at this point, you have a risk of puncture and you have the risk of some generation of heat during your lightning strike, which is obviously something we want to avoid where we have an explosive atmosphere. We also need to make an assessment of what's called separation distance, which is essentially an assessment of whether we need to bond pieces of equipment to the lightning protection system, or whether our air terminal or other part can be kept isolated. And so if we're trying to design an isolated lightning protection system, it needs to maintain a suitable separation distance from any metallic structures both inside and outside the building. And often this separation distance is quite low. It's normally only a few tens of centimeters, unless you've got a really large building like the one we're going to perhaps show you later on. Now, a problem with structures with explosive atmosphere is that they often extend beyond the structure itself. If you have, for example, an oil or gas storage tank, they quite commonly have some vents on the roof, and at times during the operation of that site, there will be an explosive atmosphere for several meters around those vents, which means that you cannot have lightning energy in the zone around that vent. It's worth knowing that there are insulated down conductor products that have an inherent separation distance. For example, Den produce one. And this can be very handy when fitting isolated lightning protection systems. It's worth having a conversation with them directly. It's quite an interesting product. And as I say, for structures taller than 60 meters, we need to continue a lightning protection system that starts on the roof down the top 20% of the structure where that's above 60 meters. So if you're building 65 meters tall, you only have to protect the first 5 meters of that building. And once we've assessed our structure and determined what parts are in need of protection and what parts are going to be included in our lightning protection system, we then apply our EGM, electrogeometric method. As Isako touched upon, there are 3 that are identified as being suitable under IEC 62305, the protection angle method, the rolling sphere method, and the mesh method. And there are other methods available in literature, but they're not currently supported by the IEC standard. There are also products available that make alternative claims that beyond what the standard suggests, but again, they're not compliant to the IEC 62305 standard. So we then have to look at the values of rolling sphere size for the different classes of lightning protection. And we have the rolling sphere radiuses, as Isako touched upon. We have our mesh density, which starts at 5 by 5 meters for a class 1 system and goes up to 20 by 20 meters for a class 4 system. We also have our protection angle graph, and this is identifying the sort of the key limitations with the protective angle method is that the protective angle method, each of these lines stops at a certain height above ground or above the reference plane. And if your structure is more than that height, then the protective angle method is not valid and cannot be used. So if you want to protect your 60-meter tall building with a class 1 lightning protection system, you can't use the protective angle method because it only applies for the first 20 meters. Sorry, this table's a little bit small. I can make it bigger if people want to go back to it at the end of the presentation. So how does a mesh method work? Well, we draw our lightning protection system. We've got our conductor that runs around the parapet of the building, and we then draw our mesh across the roof, as you can sort of see. And I just drawn a quick plan view of this to show how that conductor could potentially be routed. So the purple color here represents the lightning protection system conductor. And the mesh method has some disadvantages. Firstly, it's only applicable to plain, so simple flat surfaces. You also have to put in quite a lot of conductors, so there's quite a large material cost. And in order to install it, there's lots of working at height. And in many countries, we now have safety regulations which ask us to consider the installation process as part of our design and reduce things like working at height to reduce the hazard to the construction workers. And the final issue with this mesh method is that because your mesh comes close to lots of equipment on the roof, you then have to fit a lot of SPD to protect the structures within the building from damage due to lightning energy. And those type 1 SPD are quite expensive. So any saving you make in the design is immediately paid back in component costs for the air termination system and also for your SPD. So the protective angle method it's fundamentally a simplification of the rolling sphere method. So whereas with a rolling sphere we'd get a spherical area of protection, we get an arc that's generated. We simplify that down to produce a cone. And because we're saying we're covering a smaller area, it's somewhat conservative. You can see that we're missing all of this area that were we to apply the more rigorous rolling sphere assessment, we'd see that it was protected. And as I say, there's those height limitations that we discussed, and you can see that a bit better in this graphic here. You can see that this is the protection angle for the various different classes of lightning protection system. And so why is the protective angle method good? Well, it's really easy to evaluate in 2D. You can print out your drawing and take a set of compasses, and you can really easily draw out your lightning protection system evaluation by hand. And obviously you can do the same in CAD, but it's really good because it works entirely in 2D. But it still only works for fairly simple structures. And because the approximation is conservative, you're still spending money on lightning protection system components you don't need. And also there's a risk that because you're only doing your analysis in 2D, you're going to miss areas that need protection. And then finally, it's height limited. It only works below a certain height. So then we come on to the rolling sphere assessment. It's the most accurate assessment acknowledged by the IEC 62305 standard, and it works for all conventional lightning protection system, air terminals, and all structures, as long as you do your assessment in 3D. You can't just get out AutoCAD and draw some 2D circles on some elevations of your substation. You need to do that full 3D assessment to ensure that you're fully covering the structures you need to protect. And so using XGS Shield will always give you the most accurate result compared to other approaches. So why does rolling sphere work? Well, in the way a lightning strike happens is that there's a lightning bolt. The lightning stroke comes down from the clouds up above in these steps, and eventually it reaches this determination point where it meets a rising leader from a point that is high in potential. And it's effectively doing a radial search at that point for the rising leader. And so by modeling this radial search as a sphere, we can then assess where those rising leaders are going to come from and provide an air terminal that will intercept that strike. So let's have a look at a sort of graphical representation of a rolling sphere assessment. And this is quite an important video because it gives you an idea of the scale ratio of the sphere compared to a building that we're typically assessing. And you can see that we're rolling this ball over the building from a number of different locations to identify all the points that the building can be struck. In the past, people have described it as rolling a basketball over a building, but as I say, it's more important to think of it as perhaps rolling a basketball over a shoebox. That gives a better image of the scale ratio compared to the image you see. And you can see in this video we've picked up these points in red which are likely to be struck by lightning, which then allows us to work out where we need to put some air terminals. So why are structures with explosive atmospheres challenging? So this is a sort of a sketch of a typical oil or gas storage tank. You can see it's got a it's a cylinder with a conical roof. So other projects you've seen may look different, but this is sort of a typical example. And often, actually, these are made out of 4 or 5 mil thick steel, and so you can consider them largely self-protecting. But they have some issues, because not only do we have to protect the structure, but we also have to prevent lightning from getting into anywhere with an explosive atmosphere. So, for example, we've got this vent on the roof of the tank, and this vent has an explosive atmosphere of a few meters in radius. And that might be that it only occurs for a few hours a year. It might be called a zone 2, but the lightning protection standard requires that we divert lightning energy from entering that zone, because we don't know what when that lightning strike might happen. It might coincide with the time that vent is venting gases. And what do these zones look like in a real project? This sketch isn't really very good. Well, here's a typical drawing that you might receive from a customer, and you can see we've got this is a process plant, and you can see that actually the explosive atmosphere encircles quite a large part of the site, but it's actually limited in height, in that it's only within these structures. And so we can build those explosive atmosphere areas in XGS Lab Shield so that we can prevent the lightning from attaching to those areas. And so again, it's worth just looking at this table again, because if our tank is greater than 4 mil thickness of steel, then, or is greater than or equal to, I should say, then we only need to focus our lightning protection system on this little bit of the structure here. And we don't have to worry too much about the rest of the tank. So Isako spoke earlier about XGS Shield, which has been out for a little while, I think it's a year or so. And XGS Shield uses a simplified computation approach, which is limited in height, and it cannot assess structures more than 60 meters tall in all cases. However, we've managed to use it for taller structures by separating the structure into chunks and looking at each section in isolation. And that was quite challenging. It wasn't very easy to understand for our clients, and so we've been knocking on the team at Cint's door for a little while, saying, "Can we have a go at Shield Advanced?" And Shield Advanced uses an entirely new computational approach. It's the first tool on the market to use a rigorous rolling sphere approach, and that means that it can work for all shapes of building, including sort of oddly shaped buildings which aren't sort of rectilinear. So we then, just as Isako did, we build our model, we build it in 3D. We can do it in a CAD tool like AutoCAD. And as with any of your earthing models, obviously you need to optimize your input geometry to get the best performance. So what I will do now is I will change sharing my screen, and I will show you a few project examples in XGS Shield Advanced to show you what can be done. How do I do that? That's the button I'm looking for. Share that screen. So this is our XGS lab. So what I'm going to say, this is a beta version. It's still got a few issues, for want of a better word, that the team are working on. So please bear with me. And what I'm going to do first is I'm going to show you a quite simple project in regular Shield. copy. Let's have a look at it. Run our shield evaluation, which should only be a few seconds. Sorry about this, folks. I think this is just an issue with the beta. As I had the assessment run earlier, and then I closed it. So this project is I suppose, a fairly simple structure. This is a small substation that we did some work on recently. And we had a couple of buildings, which actually you might even recognize from Isako's presentation, and some transformers and some structures associated with them. And we were asked to design a lightning protection system that protected those. And you can see the so this is it. This is in regular shield, and you can see the protective blanket, as we like to call it, that the lightning protection system delivers from the air rods that have been placed around the site. And so if we now close this model and we open the same computation in Shield Advanced, we can perhaps see some differences. So what we'll just do, because I wasn't able to show it in the previous model, is just have a look at the structure in a bit more detail. So we'll have a look in our isometric view. And so you can see we have these two buildings here. We have some outdoor switchgear over here, and then some outdoor transformers. And then we've drawn a lightning protection system with three freestanding air rods and some roof mounted air rods on these buildings over here. And we can then run our assessment. So we're evaluating this for a class 4 lightning protection system. So we've got a rolling sphere radius of 60 meters. Shielding, I want me to run this again as well. Cute. Hopefully this should work. And so you'll notice that in Shield Advanced at the moment, we have a couple of fewer buttons, and we can only look at our sphere in 3D in the XGL view. But you'll see that the sphere, the rolling sphere assessment is broadly the same, because this is a small, simple structure. There's nothing above 60 meters in height, and so this, and we've run our assessment based on a class 4 lightning protection system. And so that, I suppose, is where XGS Shield is entirely valid and usable and works quite well. But where you might find you come into issues perhaps is in some larger projects. And so I'm just opening this new project. It's quite a large model because it's a very large project. See if it will load. And sorry about this. As I say, it's quite a large model, so it's quite challenging for the software to run it, and I'm sure with Teams and everything else that doesn't help either. So the model's just opening. I think it takes a minute or so. Interesting. Okay, I'll just let this load up quickly. Sorry about this, folks. I will record this for next time. So this project that we're going to look at is a very large factory site. It's got some buildings that are a few hundred meters long, but most interestingly, it's got in the middle of it this really tall tower. This tower is in fact almost 200 meters high, and it's pretty much integrated into the surrounding buildings. So we needed to assess all of the structures in concert to get the best understanding of the lightning protection system. Now, a further complication was that this came out as needing a Class 1 lightning protection system, which meant that actually even these buildings here, which are 30 or 40 meters tall, were too tall for regular shields to evaluate reliably. But obviously we only need to protect the roofs of those. But what that meant was that we needed to build up several models to assess the lightning protection system as a whole. But the reason I'm using this example is to show that it is entirely possible to evaluate a Class 1 lightning protection system on a really large factory site like this. You can see we have our tower. And one thing you'll notice is that you can't see our sphere going down the side of the tower. You can't see our teal blanket, and that's because it's following a true rolling sphere approach, and we haven't drawn the down conductors in this version of the model. The rolling sphere has actually disappeared within the structure, and you can see that not just on the tower over here, but also on the side of this building over here. And were we to run the same assessment in XGS Shield, it would not have done that. It would have just ignored the size of the building completely. And there's a few graphical glitches that the team are working on to improve the graphical output. But you can see that we've got an accurate assessment of the area of protection on the roof of the tower up here, and also all the way across the roofs of these buildings, which just have a conventional meshed lightning protection system on them. You can see here that the mesh isn't entirely effective, but it meets the requirements of the standard. And this is, as I say, another reason why the mesh method isn't always the best lightning protection approach. In terms of actually setting up the model, it's actually very much the same as using Shield. You will definitely get more benefit from using the 3D shapes in XGS Lab to get a better view of your building, I've built a couple of models with just the wireframe, and they're not quite as easy to understand, especially when they're on this sort of a scale. But as I say, actually using the software is very similar. And so if you've used regular Shield, you can quite easily pick up Shield Advanced. And so if I go back to my presentation now, and we go to, so why is this blanket of protection important? Well, it shows not only how effective your lightning protection system is and what parts are protected, but that also tells you where you need to fit those type 1 SPDs. And so you can make an assessment of, if I put in a couple of extra air termination rods, can I take away some SPD? And there's sometimes a quite good cost benefit argument to be made there. And so that can be quite useful, particularly in these more complicated projects. So that's the end of my presentation. I've talked about why the mesh method doesn't always work, some of the alternatives that can be used, and we talked about how the rolling sphere analysis, how rolling sphere works, and we've showed you how you can apply it in XGS Shield.